Hello friends, I welcome you all to my lecture on solution of integral equations using Fourier transforms. So let us first define what do we mean by a Fourier transform. Let by t be a function defined for all t belonging to the interval minus infinity to infinity. Then the Fourier transform of by t is defined as f by t equal to y bar s equal to integral over minus infinity to infinity e to the power I s t by t dt. The function by t is then called the inverse Fourier transform of by bar s and is written as by t equal to f inverse by bar s, and it is given by t equal to f inverse by bar s equal to 1 over 2 pi integral over minus infinity to infinity e to the power minus I s t by bar s ds. Now some authors define the Fourier transform of by t which we are denoting by bar s as also integral over minus infinity to infinity e to the power minus I s t by t dt, but then the inverse Fourier transform will be given by f inverse by bar s equal to 1 over 2 pi integral over minus infinity to infinity e to the power I s t by bar s ds. So there is no harm, we can also use this formula, and further some authors define the Fourier transform of by t which is equal to by bar s as 1 by root 2 pi integral over minus infinity to infinity e to the power I s t by t dt, and the corresponding inverse Fourier transform which is by t is equal to 1 over root 2 pi minus infinity to infinity e to the power minus I s t by bar s ds. So the coefficient 1 over 2 pi they distribute over the Fourier transform as well as to the inverse Fourier transform as 1 over root 2 pi. Now we next define the infinite Fourier sine transform. The Fourier sine transform of by t where t varies from 0 to infinity is denoted and defined as follows. Fs s denotes sine transform. So Fourier sine transform of by t is by s bar s, which is defined as 0 to infinity by t sine s t dt. The corresponding inversion formula is given by t equal to fs inverse by s bar s equal to 2 over pi 0 to infinity by s bar s sine s t ds. Again some authors define the Fourier sine transform of by t which we are denoting by s bar s as root 2 over pi 0 to infinity by t sine s t dt, and the corresponding inverse Fourier sine transform of by s bar s as square root 2 over pi 0 to infinity by s bar s sine s t ds. So the coefficient 2 over pi they distribute as root 2 over pi here and root 2 over pi here. Now infinite Fourier cosine transform is defined in a similar manner. The Fourier cosine transform of by t where t varies from 0 to infinity is denoted and defined as FCC denotes cosine transform. So Fourier cosine transform of by t is equal to by c bar s is equal to integral 0 to infinity by t cos s t dt. The corresponding inversion formula is given by t equal to fc inverse by c bar s equal to 2 over pi integral over 0 to infinity by c bar s cos s t ds. As in the case of the Fourier sine transform, some authors distribute this 2 over pi as root 2 over pi here and root 2 over pi here. So they define Fourier cosine transform of by t as by c bar s equal to root 2 over pi integral 0 to infinity by t cos s t dt, and inverse Fourier cosine transform of by c bar s as root 2 over pi 0 to infinity by c bar s cos s t ds. Just like in the case of Laplace transform, the Fourier transform and Fourier sine and cosine transforms also satisfy the linearity property. So Fourier transform of c1 by 1 plus c2 by 2 where by 1 by 2 are functions defined over the interval minus infinity to infinity is equal to c1 by f by 1 t plus c2 f by 2 t, and here by 1 and by 2 are functions defined on the interval 0 infinity. Then the Fourier sine transform of c1 by 1 plus c2 by 2 is Fourier sine transform of c1 by 1 plus c2 by 2 equal to c1 times Fourier sine transform of by 1 plus c2 times Fourier sine transform of by 2. c1 c2 are constants. Now in the third equation we are writing the linearity property for the Fourier cosine transforms. So Fourier cosine transform of c1 by 1 plus c2 by 2 is equal to c1 times Fourier cosine transform of by 1 plus c2 times Fourier cosine transform of by 2. So these properties of the Fourier transform and Fourier sine and cosine transforms are easily verified by their definitions. The change of scale property, like in the case of Laplace transform, here also we have the change of scale property. So if by f by t equal to y bar s, then f by a t is 1 by a by bar s by a. So and similarly Fourier sine transform of by t, if it is by s bar s, then Fourier sine transform of by a t equal to 1 by a by s bar s by a, and Fourier cosine transform of if it is by t, if it is by c bar s, then Fourier cosine transform of by a t is equal to 1 by a by c bar s by a. So these properties are also verified easily by just by following their definitions. Now let us define the convolution of two functions. Just like in the case of Laplace transforms, the convolution here is of two functions gx and hx, which are defined over the interval minus infinity to infinity, is denoted and defined as g star h equal to integral over minus infinity to infinity gx ht minus x dx, and this is same as integral over minus infinity to infinity gt minus x hx dx, which can be easily verified. So then the Fourier transform of the convolution of g and h, that is f of g star h, is the product of the Fourier transforms of gx and hx, just like as in the case of the Laplace transform. So this is how we get the Fourier transform of the convolution of two functions of x. Then like in the case of the Laplace transform, we have shifting property here. If by s is the complex Fourier transform of by t, then the complex Fourier transform of by t minus a is e to the power I s a by bar s, which can also be easily shown proved by following the definition of the Fourier transform of by t. Now let us see how we can solve the integral equations using the theory of Fourier transforms. So let us take this equation, integral 0 to infinity f t cos s t dt equal to 1 minus s 0 less than or equal to s less than or equal to 1, 0 when s is greater than 1. So here this is nothing but you can call it as FCS, because we can identify this equation by the Fourier cosine transform of the function ft. In the Fourier cosine transform, if you go to the definition of Fourier cosine transform, then you will see that fc by t, which we have denoted by c bar s, is integral 0 to infinity by t cos st dt. So in place of by t here we have ft, so we are denoting the integral 0 to infinity ft cos st dt by fc bar s. So here we are given fc bar s, and we want to determine the unknown function ft. So we will use the inversion formula for the Fourier cosine transforms. So ft is equal to fc inverse fc bar s, which is equal to 2 upon pi 0 to infinity fc bar s into cos st ds. Now this is, let us use the definition of fc bar s. Fc bar s is 1 minus s over the interval 0 to 1, and elsewhere it is 0. So this integral over 0 to infinity will can be written as integral over 0 to 1, and fc bar is equal to 1 minus s cos st ds. The remaining part, the integral over 1 to infinity vanishes, because fc bar s is equal to 0 for all s greater than 1. Now let us integrate it by parts. So when we integrate it by parts, what we have, 1 minus s integral of cos st is sin st. We are integrating with respect to t, we are integrating with respect to s. So this will be sin st over t, and we are to evaluate the value of this expression over at 0 and 1, minus integral 0 to 1, derivative of 1 minus s is minus 1, and then sin st over t dt. Now when s is equal to 1, this is 0, and when s is equal to 0, sin st is 0, so this expression vanishes, and what we have is 2 over pi integral over 0 to 1 sin st over t ds. Now we can integrate it again, so 2 over pi t we can take out, and then we have minus cos st over t. So this is nothing but 2 over pi t, and then this is 1 minus cos t over t. So what we have is 2 over pi t square 1 minus cos t. So this is the solution of the given integral equation. We have found out the unknown function f t. F t is 2 over pi t square 1 minus cos t. So this is the answer of this question. Now let's go to the second question. So here we have the integral equation 0 to infinity f t sin st dt equal to 1 when 0 less than or equal to s less than 1, 2 when 1 is less than or equal to s less than 2, and 0 when s is greater than or equal to 2. So again let us, so this is Fourier sine transform, so this we can denote as fs s. Now let us go back to the inversion formula for the Fourier sine transform. So the inversion formula for the Fourier sine transform is here. So here we have integral 0 to infinity by t sin st dt as by s bar s. We have here integral 0 to infinity f t sin st ds. So in place of by t we have here f t, and we have to determine the known function f t. So let us see, f t is given by fs inverse fs bar s, and which is equal to 2 over pi integral 0 to infinity fs bar s into sin st ds. So this is 2 over pi integral 0 to 1 fs bar s is equal to 1, so sin st ds plus integral 1 to 2 sin st ds, and over integral 2 to infinity fs bar s is equal to 0, so 0 sin st ds. So this is equal to 2 upon pi, and we have minus cos st divided by t here 0 to 1, and here we have 2 times minus cos st divided by t. This is 0. So this gives us 2 over pi into t 1 minus cos t, we get 1 minus cos t here, and we get 2 times when you put 2 here we get cos 2t, when you put 1 here you get cos t, so cos t minus cos 2t. So this gives you 2 upon pi t 1 plus cos t minus 2 cos 2t. So this is what we have, ft equal to 2 over pi t 1 plus cos t minus 2 cos 2t. Now let us do one more question on this to make things more clear. So suppose we have to solve integral 0 to infinity ft cos st dt equal to e to the power minus s. So again we are given the Fourier cosine transform, we get denoted by fc var s, then the unknown function ft is given by 2 over pi 0 to infinity fc var s into cos st ds. So this is 2 over pi 0 to infinity e to the power minus s cos st ds. Now we can make use of the known formula. This formula is known to us. Let's use the formula integral over e to the power at cos bt dt equal to integral over is equal to e to power at a square plus b square a cos bt plus b sin bt. So this is equal to 2 over pi. When we use this formula, a is equal to minus 1, instead of t we have s here. So e to the power minus s divided by a square plus b square, and a is equal to minus 1, so minus 1 whole square, and b is t, so we get t square. B is t. So then we have a cos bt, so a is minus 1 cos, b is t and t is s, so st plus t sin st. This is what we have. So when s goes to infinity, because cos st is bounded by 1 and e to power minus s goes to 0, so this quantity goes to 0, and then e to the power minus s into sin st when s goes to infinity also goes to 0, because sin st is bounded and e to power minus s goes to 0. So this goes to 0. Now we have 2 upon pi, and then we put the lower limit. So minus e to the power 0 is 1, so 1 upon 1 plus t square, and then here we put t equal to 0, sorry, s equal to 0, so we get minus 1, and then we put s equal to 0, this becomes 0, so we get 2 upon pi into 1 plus t square. So we get ft equal to 2 upon pi into 1 plus t square. So this is how we solve the integral equations using Fourier transforms. Now in our next lecture we will see how we can solve Cauchy integral, how we can solve integral equations using Hilbert transforms. With this I would like to conclude my lecture. Thank you very much for your attention.